Hi, I'm Alex Alvarez and welcome to Dynamics 4. In this tape we're going to be talking about rigid bodies as well as dynamic constraints. Rigid bodies are a way to take any NURBS or poly piece of geometry and turn it into something that you can apply fields to so that you can have Maya create simulations where it'll animate things for you, saving yourself a lot of time. So whether you're trying to do something as simple as a bowling alley or trying to get a character to pick up an object which it then throws, where when it throws it, what happens to the object is completely figured out by Maya. You can really do a wide range of stuff. And the dynamic constraints are used to simulate mechanisms that exist in the real world, such as a door hinge or a spring that you might see like in a shock absorber of a car. A lot of different things can be done using the dynamic constraints. And so we'll be looking at a variety of examples explaining all the different attributes that you have. And there you go.
Okay, in this tape we're going to talk about rigid bodies, and what I have up in this scene is an example of a rigid body simulation that's also using dynamic constraints. And rigid bodies are a way to create simulations which basically will save you the time of having to manually animate something like this yourself. So everything that we're looking at right now as far as the motion of the catapult, the ball, and then the way the crates are being hit and bouncing around is all being calculated completely by Maya. And so it's just a matter of understanding all the different attributes that exist and the way they work together that you can determine how to balance out the performance with all the different settings that you have to end up with a wide variety of results. And so we can see that I also have the ability to scrub through what I'm looking at and through the simulation, which is because I've cached this data. And so to look in, just to get some of the basic terms understood before we start explaining everything, is what we see there is this catapult. That's an example of dynamic constraints where we can see we have hinges that are operating in there determining how the catapult behaves, as well as something called a spring, which is basically a spring that's releasing the catapult. Then we can see that we have something like this ball that's being thrown, and that's an example of something called an active rigid body, meaning it can behave with collisions, it can be affected by fields, and then we'll see that it hits all of these crates. These are also active rigid bodies, but then you'll notice that the ball and all the crates are bouncing on the ground and against the walls. Those are examples of passive rigid bodies. So rigid bodies are elements that can collide with each other and be affected by fields, and then the difference between passive and active is a passive rigid body is something that will not be affected by the collision, meaning that things can bounce off of it but it will not move. And then these crates and the ball are examples of active rigid bodies in the sense that they will be affected. And so what we're going to do is I'm just going to go and we'll start with a relatively straightforward scene where I'll just open up, let's say, a simple example where we just want to get this cylinder to fall down these stairs. And if I hit play right now, we'll see that I don't have anything in the scene. The first thing you're going to need to make sure you do is go to your animation preferences, make sure that your units are set correctly, so let's say I want to work at 30 frames per second, and then go to your timeline and make sure that your playback speed is set to play every frame, because if you set it to real time you will not get accurate results. Play every frame is necessary because a dynamic simulation builds itself on every frame, meaning that what's happening at frame 10 is based on what's happening at frame 9. So if you set it to real time, it's going to skip frames, and that's going to give you a different simulation. So playback speed again is set to play every frame. And so because of that, when you want to see your simulation with the correct timing, you're either going to need to cache the data into memory or you're going to need to do a play blast. So I have it set to play every frame. I'm going to save this. And so now what we're going to need to do is figure out how you turn something into a rigid body. In this situation I have a NURBS object as well as some poly objects. Dynamics can be calculated on either NURBS or polys. It's just with NURBS, there's a couple things that you need to keep in mind. The first thing is you want to, across the board, whether it's NURBS or poly, is delete history on your objects. If you have any construction history, it can cause things to behave unpredictably. Also, if you have a NURBS object, you want to avoid trimmed NURBS geometry as collision objects because objects, if you trimmed a hole out of this plane, for example, a rigid body would not be able to fall through the hole if it was a trimmed NURBS surface. And so what you would do is you would convert that trimmed NURBS surface to a poly object and use that poly object as your collision model, even though you might still render the NURBS object. And so at this point, what we're going to want is I'm going to get my timeline to show me, let's say, 300 frames. And then going back to frame 1, we need to specify in the scene how things are going to behave. First off is I know that I want this to fall down these stairs and bounce on the ground. But based on what I just mentioned in that catapult scene, the cylinder would be an active rigid body, while the stairs and the floor would be passive rigid bodies. And so also what we want to do is notice in here that I have the floor intersecting with the stairs. That is okay to do if you're dealing with passive rigid bodies. But if you have active rigid bodies, you need to make sure that at frame 1 they are not intersecting. And so what I'm going to do in here is just make sure that the floor and the stairs are not intersecting so that I can avoid collision errors if I decide to turn the ground into an active rigid body, just so I can show you what would happen if we did. So at this point back at frame 1, we need to be in dynamics mode. And what I'm going to do is select first, let's say, the ground. For the ground in dynamics mode, let me just hide the shell for a second. We can go to the soft/rigid body pull down menu, and in here you'll see that you have at the top create active rigid body and create passive rigid body. If you go to the dialog box for either of these, you'll see that the dialog boxes are exactly the same. The only difference is that you have this active checkbox, and so if that's checked, we'll create an active rigid body, and if you uncheck it, we'll create a passive rigid body. So I want the ground to be passive, so I'll make sure the active checkbox is not checked. And we will see that there are a lot of attributes that are in here. You can change all of these after the fact, and so we do not need to actually make our decision right now about any of the attributes that are in here. And so leaving everything at the default settings, I'm going to have the ground become passive, so I'll hit apply. And then in here you'll see that it's telling me the floor actually already has a rigid body node. And so that's just because if I go to the outliner, it means that when I save this scene, I'd already turned things into rigid bodies. And so I can actually see I have some rigid body nodes in the outliner. I'm going to delete them, and then I'll explain to you how what I just did in a second. And so I'm going to go back to frame 1, select the ground, and choose Create Passive Rigid Body. Then I will select the stairs, Create Passive Rigid Body, and then select the cylinder and Create Active Rigid Body. If you want, you can select multiple objects at the same time. In the sense, I could have selected the stairs and the floor and said Create Passive Rigid Body. So now if I hit play, we will still see that nothing is happening, because even though I've assigned things as being rigid bodies, we do not have any fields in the scene. If we open up the outliner, we will be able to see, as I just mentioned, that if you go to Display Shapes, you will be able to open these objects up and see that all 3 of the surfaces in our scene now have a rigid body shape node associated with them. So you can see there's the stairs, the shape node for the geometry, and then the shape node for the rigid body. So if you wanted to turn these objects into regular pieces of geometry, meaning you wanted to get rid of their rigid body nature, you could do what I just did before, is just select that rigid body node and hit delete. So by deleting those rigid body nodes, my geometry is going to be back to normal. So again, let's select these 2, create passive, select the cylinder, create active. So at this point, what I want to do is I want to figure out how I can go in and get that cylinder to behave. Well, what you can do, and it's going to be similar to particles, is you can select these rigid bodies and apply fields to them. But they also have some default attributes that can give them an initial velocity in a certain direction or an initial spin. So first let's deal with just some simple gravity. Maybe I'll select the cylinder and apply gravity to it. If the cylinder is selected when I create a gravity field, that gravity field will automatically be connected to that cylinder. And if I hit play, we will see that it's working. And now it just sort of fell over and came to rest on one of its ends. Okay. If I delete that gravity field and then create another one without anything selected, what we will see when I hit play is nothing will happen. You would have to go to the Dynamic Relationships Editor under Window, Relationship Editors, Dynamic Relationships, and then manually select the cylinder on the left and then select the gravity field on the right to connect them. So now if I hit play, again we can see that cylinder will fall. If I wanted to have that cylinder give it some sort of push to the right in the X direction, I could select the cylinder and then maybe also assign a field to it, like a, let's say, uniform field. I could give it a uniform field that's maybe pushing it in the X direction that maybe I keyframe the magnitude on. So I'll switch to Sept keys, keyframe the magnitude with a value of 5, but then maybe at frame 10, I'll turn that uniform field off. And if I hit play, we'll see that we've given that cylinder a little bit of a push by using a uniform field. And now we're going to see that it's going to fall down those stairs and then come to rest on the ground. So basic rigid body simulations like this are actually quite easy to do in Maya by just understanding the difference between rigid bodies as far as passive and active. Other things that you need to check in this scene is also, for your surfaces, you got to know what direction the normals are pointing in. If I select this NURB surface, I can go to Display, NURBS Components, and in here I can turn on the normals. And we can see that the normals for these stairs are pointing this way. Collisions will only occur on the side of the normals, and so you have to be very aware of that. If I selected this surface and switched the normals so the normals were pointing in the other direction by reversing the surface direction, if I hit play, you're going to see this happen. That cylinder fell, but then got stuck on the surface because it's not colliding correctly, and your simulation will stop and you'll get an error message saying that your rigid bodies are interpenetrating. And so to correct that, I would just select the stairs and reverse their surface direction. So now we can see when we hit play that things are behaving correctly again. So now we need to look at some of the attributes that these rigid bodies have to determine how bouncy they are, what their mass is, any friction settings, and so forth. So what I'm going to now do is let's delete that uniform field so that when I hit play, that cylinder just falls down but doesn't have any lateral movement to it. If we select that cylinder, we will be able to see, if we look in the channel box, that it does have many attributes on its rigid body node. And we're going to go through these relatively quickly because some of them are quite intuitive and we do have a lot to cover. And so the first things we'll see for that cylinder, it has attributes called initial velocity and initial spin. Initial velocity is something that you could use instead of a field. And this is something that's only going to give it a push or a velocity at frame 1. It's not going to give it a constant acceleration. So if I go to the cylinder and say it has an initial velocity in the x direction of, let's say, 5, if I hit play, now you can see that cylinder is moving in x. If I give it initial velocity in y of 5 as well as x of 5, you'll see it's going to hop up a little bit before it actually comes down. So that's initial velocity. Very straightforward to give things an initial direction without having to go and create a field. But again, this is something you would not keyframe as far as the initial velocity or the initial spin. These are just attributes that you'll have at frame 1. So if I gave that cylinder an initial spin, let's say in z of, let's say, 90, and I hit play, you're going to see that that sort of was spinning backwards. Let's give it, let's say, negative 200 in z and hit play. You can see that initial spin that it was being given. Then we'll give it an initial velocity in an x, maybe the initial spin negative 500 in z, and let's hit play. And you can see that behavior as far as the initial velocity and the initial spin settings. Then in here, I'm going to set all the initial velocity and spin settings to 0. You have something called center of mass. Center of mass does determine where the center of mass is of that object, where, let's say I created something like a sphere. And for this sphere, this is just a NURB sphere right now. I'll scale this up a little bit. And I'll turn this into an active rigid body. So we'll go into dynamics mode, active rigid body, and I'll connect gravity to it. So that now we will see this. Automatically, when something is turned into a rigid body, it will automatically collide with any other rigid bodies in the scene. But for this sphere, you will see if you go into wireframe mode that there's going to be a little X at the center of that object. It's very hard to see, but it's there. That X is the center of mass, and by default, that'll place itself at the center of all of the vertices of that node. You can actually change where the center of mass is located by selecting either center of mass X, Y, or Z in the channel box and moving it by middle mouse button dragging. So if I select center of mass Y and middle mouse button drag, we'll be able to see that X move, let's say, from the top pole of the sphere to the bottom pole. I'm going to move the X to the bottom pole of the sphere so that now the center of mass is down here. If you think of one of those punching bags that are filled with sand so that when you punch them they always right themselves up, that's kind of what we'll get as far as the performance of this rigid body now. So when I hit play, notice how that sphere is behaving differently, as if it's heavier at the bottom of that sphere, and so it's continually trying to right itself up. And so that's the basics of center of mass. Another thing to keep in mind, though, is that you'll see that if we look at the bottom, we have an attribute called lock center of mass, which is off by default. If you make any changes to the shape of this sphere, so I go and move some of the vertices, it'll change where the center of mass is located, as the center of mass, when you go back to frame 1, will try and position itself again at the center of those CVs. You can get the center of mass to not do that if, again, you just select that rigid body node and turn on lock center of mass, so that if you make a change to the shape node, it will not move where the center of mass is located. Okay. So, but also along the lines of what I just talked about as far as moving the CVs, when you use rigid body dynamics, you cannot change the shape, meaning doing something like this or non-proportionally changing it. You cannot change the shape of that object in an animation, meaning that I can change its shape at frame 1 and hit play and see that it's going to behave differently. And so notice that just that change that I made, we now get a different simulation on that sphere. But I could not, let's say, animate the scale of that sphere and expect to get an accurate simulation. Rigid body dynamics use the shape of the object at frame 1. If you need an object to change shape because of the collision, or to change shape while it's colliding or falling with fields, you would need to use soft bodies. And so we're not going to be able to do that with these settings in here. And so again, we can see the settings in here on that sphere. Also along these lines, let's say I went and created something like a cylinder, and I sort of flattened this out a little bit. If we were trying to do something like, a subway, let's say we're doing something like a coin that needs to roll around, or a manhole cover that needs to spin, you can see I could take this, get this to maybe be positioned a little bit like this, turn that into an active rigid body, connect gravity to it, and hit play. And you'll see that automatically it's going to give you realistic behavior. If I wanted to add a little bit spin to it, I could go to its initial spin in Y, and then maybe add a little bit there, so that now when I hit play, it's got a little bit more of that kind of rolling motion, like the way a quarter would come to rest and whatnot. So let's get rid of that cylinder and go back to these settings and take a look at some of the other attributes. Aside from our initial velocity, initial spin, and center of mass, we then have attributes called impulse, impulse position, and spin impulse. Impulse is something that you can keyframe, although you'll tend to find that you'll prefer using fields instead of using the impulses. Impulses are something that will, if you turn them on, give a constant acceleration to your rigid body until you turn them off. So for example, if I go and hit play in here, we'll see that cylinder is not really moving laterally very much. So let's say I wanted around frame 100 for that cylinder to hop up in Y and move in X. I could go to the impulse, and then let's say use stepped keyframes, keyframe the impulse, go to frame 100, and then maybe turn on the impulse in X, and turn on the impulse in Y, and set another keyframe. And then maybe at frame 110, I'll turn them off, and keyframe those again. Now when I hit play, we'll see what happens when we get to frame 100. You'll notice that it hopped. And so we only needed the impulse to be on for 10 frames to create a rather large movement in that X and Y direction. Because if you just left it on, every frame more acceleration would be given, or more impulse would be given to that rigid body. Along these lines, you'll see that we also have spin impulse. If I go in here and let's say delete the animation I put on the impulse, and also before we get to spin impulse, beneath impulse we have impulse position. That is determining an offset from where the impulse is coming from. By default, when we keyframe impulse, it's adding an impulse to the object based on where the center of mass is. But we can offset that in X, Y, or Z by changing the impulse position. This starts to get very non-intuitive if you try and use impulse and impulse position, because it becomes very mathematical. You end up trying to have to figure out what the vector is that you're specifying by entering in values, which again is why you'll find fields to be more useful. But let's say I go in here and just give this object an initial velocity, not an initial impulse, or not an impulse, but an initial velocity in X, so that it's moving down the stairs. But then let's say around frame 180, I want that object to start spinning. What I can do is go to my spin impulse, keyframe those, hit play, and then let's say once I get to around frame 180, I will turn on the spin impulse, maybe in the y-axis, with a small value of 2, and keyframe those on. And let's see what happens if we just leave them on, we don't keyframe it turning off. Once we get to frame 180, we're going to see it start to spin. And you'll see it just starts to spin faster and faster and faster because that impulse never turns off. So what I could do is maybe go a few frames after 180, turn the impulse to 0, keyframe it again, so that we can just go and see the object fall down, rest down on the ground, and then spin. But then eventually it'll lose its speed because the impulse turned off. So that's pretty much it as far as initial velocity, initial spin, center of mass, impulse, impulse position, and spin impulse. So again, we went through them kind of quickly, but you should find that they're very, very easy as far as these attributes go. The next things we're going to want to start talking about are the attributes we have beneath all these impulses and initial velocities, and we are going to start with where it says mass. In this scene, mass is not going to really come into play, and so let's work with something different. If I went and opened a scene, let's say, that had some boxes in it, and so we can see we have these crates, and I'm also going to give myself a ground plane, and so let's scale this up a little bit. And then with this ground plane in here, I'm going to turn the ground plane into a passive rigid body. Make sure it's not intersecting those crates. And also what we need to do with these crates is make sure that they are not intersecting each other at frame 1. So notice that I've left a gap between the crate and the ground. And then also between this top crate up here and the next crate down. It's very important to let your rigid body dynamics settle. And so you basically have a run-up. Because if they were intersecting, you'd get an error message. So what I'm going to do in here is maybe let's get this box a little bit closer in here. And now let's create a sphere. And we're going to sort of throw the sphere towards the crates to see what we can do with that. And so if I go into my outliner, I'll be able to see that none of my objects are rigid bodies right now except for the ground. I'm going to select all of those crates, turn them into active rigid bodies. Then I'm going to select the sphere, turn it into an active rigid body, and then I will select everything except for the ground and connect a gravity field to them. If I now hit play, what we will see is the crates will settle, so you can see that initial settling of them, and that ball will fall towards the ground. Then what I'm going to do is select that sphere and give it an initial velocity to push it towards the crates. So I'm going to give it initial velocity in the negative x direction. So let's say negative 20 in x. And if I now hit play, what we're going to see is this. And so notice how that sphere moved in and hit the crates. Well, each of these objects right now has the same mass. Whenever you turn something into a rigid body, you'll see that they each have a mass of 1. Well, if I go in and select the sphere, I can change its mass. Let's say I gave it a mass of 0.1 and hit play. What we will see is that it barely moves the crates. So by changing the mass, you can basically change how heavy your objects are. If I give the sphere a mass of 50, and each one of these crates only has a mass of 1, what we will see now is that those crates do not slow down that sphere at all. So that's the basics of mass. It makes a very, very big difference. So if you really wanted things to be a little bit even more natural, you could give each one of these crates a different mass, maybe saying that each one of them is filled with a different type of object and some are heavier than other ones, and it would give you more of a dynamic or more interesting result. Then in here underneath mass, we have bounciness and damping. Bounciness is how bouncy these objects are. If I go in and select these crates, right now they have a default bounciness attribute of 0.6. If I set the bounciness to 0 and I hit play, as you would probably expect, and let's also take that sphere and give it a lower mass setting, so maybe a mass of 10. And let's hit play. So again, each one of these crates has a mass right now, or a bounciness of 0. What we will see is they basically will fall, but there's basically no bouncing going on. You will get a small amount, but practically none. As opposed to if I go to the bounciness and give it a value of 1. And remember the default was 0.6. With this bounciness setting, you can see a very different behavior. So if these really were crates, they obviously would not bounce like that if these objects each weighed a couple 100 pounds. Then in here, let's say we gave them a bounciness value greater than 1, like a value of 2. Then you're really going to get something unrealistic, meaning that they're going to bounce. And notice, let's say I actually for a second turn off the initial velocity on that sphere. Notice with the bounciness of 2, these objects never settle. They just fall, and instead of settling, bounce, and then will bounce more and more and more because their bounciness has a value greater than 1. So for realistic settings, you'd always keep bounciness to a value less than 1. So let's select those crates and then set the bounciness to a value of, let's say, 0.5. Another thing you can then do in here to control the way they're behaving is use damping. And damping is something that can get things to mellow out, in the sense that damping is kind of like a dragging or dampening force that it's applied to these rigid bodies at all time. It basically slows them down. By default, damping is at 0. So if I put the bounciness to 1, we will see that these crates are going to be relatively bouncy. But what we could do is then add a little bit of damping on top of that, let's say 0.4, which is going to get those crates to have some bounciness, but at the same time, they will lose energy a lot faster. This can be very useful with damping when you are trying to get things to settle. Because if you have a high bounciness value without any damping, sometimes you will find objects jiggle and they never actually come to rest. So by adding a little bit of damping, you can get them to lose that energy a little bit faster and behave a little bit more realistically. So our damping right now is 0.4, maybe I'll put it down to 0.1 and then hit play. And so now you can see they are bouncy, but they do lose their energy in a more realistic fashion. The next thing underneath damping that we have is friction. Friction, you'll notice, has two attributes: static friction and dynamic friction. Static friction is friction at rest, and dynamic friction is friction while moving. I tend to change these two attributes together, as I find it more intuitive to just think as a general friction on these objects. But these are attributes that can be keyframed, as are all the rest of them, so that you can have an object get stuck onto a surface and then start to slide later on. Because if you were doing an animation where, let's say, a surface was becoming covered in oil and becoming slippery, you could then, while the oil, which is maybe done via a bump map and a specular map, as that oil moves across the surface, you could then start to lower the friction on the surfaces that are resting on it. And so, in order to take a look at friction, what I'm going to do in here is, let's say we go in, and I'm going to take this ground plane and tilt it a little bit. And let's lower it down so that nothing is intersecting. When I hit play, we can notice how these crates are behaving and how they are all sliding. I'm going to just turn on wireframe on shaded. They are all sliding down the ground. They do have friction right now. Now, both these objects, the passive rigid body and the active rigid bodies, all have friction settings. But what's controlling how these crates are sliding down that plane is not the friction on the plane. It's just the friction setting on these boxes. So if I select all the boxes, I'm going to go in and set the friction to 0. What you'll expect is they'll just slide faster down that surface. But if I take these crates and set their friction to a value of 1 and hit play, you'll notice that what's going to happen is they're basically going to fall. They'll roll a little bit, but then they'll come to rest on that slanted surface. So even though the surface is slanted and they have gravity, they're not moving because of friction. So this obviously, like mass, bounciness, and damping, is an attribute you need to set based on what you're trying to do. But as I mentioned, if I went in here, I could go in, keyframe my friction attributes on these objects. I could set keys so that I've keyframed each of these crates' friction attributes. Then I could go in, play a few frames, but then maybe like around frame 180, I'll turn the friction off and keyframe that. If I play from this point, what we're going to see is that these objects right here are going to just continue to slide. And then these objects are beginning to slide. It's just when the friction went from 1 to 0, those objects were already at rest, and so they're going to have to speed up. And now we're seeing that behave. Actually, I forgot to set the friction value at frame 1, but you get, or a keyframe, but you get the point as far as our friction attributes. The next thing we have underneath friction is something called collision layer. Collision layer is something that determines what collides with what. All objects by default are on collision layer 0, which means that they will collide with each other. So instead of using the dynamic relationships editor to determine what collides with what, with rigid bodies you use collision layers. So if I go in here and select, let's say, all of the crates and put them on collision layer 2, and then the plane or the ground is on collision layer 1, when I hit play, we will see that they do not collide with each other. But if I select this crate right here and put it on collision layer 1, we'll get this. It will bounce, but the other ones will go through. Collision layers can be used to optimize your performance in a scene, whereby if you had a scene, let's say that looked like this, where I've got, let's say, one group of crates that I'm just going to move to the side a little bit, and then I'm going to import another group of crates so that I have 2. Then I'm going to create a ground plane. And then I'm also going to create in here a dividing wall. So I'm just going to create a cube that I'm going to scale out this way and scale up this way. I'm creating a situation, and let me just scale this down so that we have more of a wall, where let's say we were trying to do something where I'm going to go in here and move this wall. Let's turn on wireframe on shading. And then I'm going to create a couple spheres. So I'll create one sphere over here, another sphere over here. Move these up a little bit. And I'm going to get these spheres to move towards those crates. Well, now I need to set everything up as far as my rigid bodies, because nothing in here is a rigid body yet. So basically, the wall and the ground will be passive rigid bodies. And then all of the crates and the spheres will be active rigid bodies. I will then connect all of those objects to the same gravity field, and then for both of these spheres I will give them an initial velocity of -z and maybe increase their mass a little bit, so that when I now hit play I get this. And actually we can see that all of these crates don't get hit by that sphere, so maybe I'll go in and move them a little bit so they are more in the path of that sphere. So now we're seeing this. Well, we have a situation that these crates on the left are never going to come in contact with the crates on the right, because there's a wall dividing them. But Maya is still calculating these objects as far as their relationship to each other to make sure they're not colliding. You can speed up your playback by putting these objects on the right and the objects on the left on different collision layers. So I can select all the crates on the left and put them on collision layer 1. Then select all the crates on the right and put them on collision layer 2. Then I would select that sphere on the right. It would also be on collision layer 2. And the sphere on the left would be on collision layer 1. But when I hit play, we're going to see this. Those crates are going to go through the floor. So you have to decide for the wall and the floor, what collision layer would they be on? Well, since both groups of crates are supposed to collide with the floor, or the same floor, what we can do is put the floor on collision layer -1. Collision layer -1 is something you can enter so that that rigid body will collide with anything. So the floor is -1, the wall is -1, the crates on the right are 2, and the crates on the left are on collision layer 1. And now when I hit play, what we will see is the playback's a little bit faster. We get the exact same simulation, but this time we've optimized our performance. The next thing underneath our collision layer is something called stand-ins. For stand-ins, I'm going to go and create a new scene so we can talk about these just to see how stand-ins can also increase our performance. So stand-ins are a way to basically get a rigid body to be calculated based on a different shape than its actual shape. And if we went in and, let's say, created something like a sphere, I'm just going to create a polysphere, we could actually get this sphere's dynamics to calculate as if it was a cube, for example. And so if I went in and turned the ground into a passive rigid body, turned the sphere into an active rigid body, and if I go in here and, let's say, we scale that a little bit, and then I'm going to go and turn on wireframe on shaded and add a gravity field so that when we hit play, we can see how things are behaving. Well, if I go and take the sphere and go to where it says stand-in, I can enter cube or sphere. You only have two options, or three: none, cube, or sphere. If I choose cube, we will see that the sphere's collisions are calculating as if it was a cube. And then obviously if we chose sphere, it wouldn't make a difference. The idea behind this is to speed things up, because what it's going to do is it's just going to use a simple primitive cube or sphere that are very low res, so that if you had, let's say, a box that you modeled that was relatively heavy because it had a lot of latches and bolts and modeled details on it, but the thing is that its dynamics would look pretty much the same if you just used a primitive cube as a collision model. That's kind of the idea. But I tend to not use these stand-ins. What I tend to do is make my own stand-ins. And what I mean by that is, let me just open a scene which is an example of that. So I'm just going to jump in real quick and grab a file that's basically showing a NURBS object. And in this case, we have this staff. And so let me just go and turn wireframe on shaded and up the display res on these surfaces. And I'm going to hide the grid. So I have a NURBS staff right now, and we will see that this is actually consisting of multiple pieces of geometry. Well, what we can do first of all with rigid bodies is you're allowed to group objects together. And if you take multiple objects and group them together, they will behave as one. And so something that's actually useful that I should show first along those lines is that if I went and created a NURBS cube, something that you should be aware of with something like a NURBS cube is that it actually has different pieces of geometry for each face. So that if I took this cube and just selected it by choosing the default pick mask and turned it into an active rigid body and connected gravity to it, and then I can turn the ground into a passive rigid body, if I hit play, we're going to see this. We're going to see that cube break apart because each face was turned into its own active rigid body. And then the simulation is going to fail because the faces do not have any thickness. And so the normals are only pointing out on one side, and so they intersect and you get an error. So for something like this cube, what you would do is instead of using this, turning it into a rigid body the way I did, I can still use something like a default NURBS cube like this, where it has separate faces. But what I can do is instead of going in and selecting each of the faces, like I've just done in the hypergraph, you can select that parent transform node, because all of these faces are grouped together. So you can group multiple things together, turn that into an active rigid body, and if I then apply a gravity field, what we will see is they won't break apart, because now this object has been turned into a rigid body, but as the group. And so for the example that I opened where I had that staff, let me get that back real quick, and what we can see in here with that is that I took multiple NURBS objects and grouped them together. But at the same time, let me just go and increase the display res again. We can see that when I play back the simulation, it's actually playing back very quickly, and I'm just getting that staff to fall with gravity. But if you actually took multiple NURBS objects like this, including some of the trimmed surfaces that I have in here, it can behave relatively slowly. And so what I tend to do is use stand-ins, but I basically model my own low-res stand-in. And in this case, if I open up the outliner, what we will see is that if I hide my high-res staff, I'm going to then display my low-res staff. And we can see that this is actually what's having the dynamics calculate on it. And so what I have done is I just created some simple poly pieces of geometry that represent the basic shape of that staff. I then group those three pieces of geometry together and turn that into a rigid body. I then make sure that the pivot point of that low-res staff matches the pivot point of the high-res staff and that their local rotation axes line up. So that way what I can do is apply the dynamics to the low-res staff, but then I can go and constrain using point constraints and orient constraints, the high res to the low res. So if I go in and delete my constraint nodes and get my high res staff to be visible, what we will see for that high res staff, if I go into the hypergraph, is that it does have a bunch of different pieces of geometry. It has a couple of emitters parented to it. It has a couple lights that are parented to it as well. And if I hit play, we'll see that now that I deleted the constraint nodes, the high res staff is staying behind. Well, what I can then go and do is select the group node that represents the low res staff, and then control select or shift select the high res staff. So you select the constraint object first, then select your high res object, and then in animation mode, not in dynamics mode, we're going to go to the constrain pull down and choose to do a point constraint and an orient constraint, because point does translation and orient does rotation. So for the options of both of those, I'll have the weight value at 1, constraint operation will be add targets, and I'll apply a point constraint, and then with the same object selected in the same order, I will apply an orient constraint, so that now if I select my high res staff, we can see it has a point constraint node and a orient constraint node associated with it. So that now when I hit play, we can see they're moving together. And so if I then hide the low res staff, even though it's hidden, it'll still be calculated. And now we can see we're getting very fast performance on my high res staff by just using a stand-in or a proxy object. So this is really the way you want to set up most of your dynamic simulations, especially when you have heavy geometry. Because you'll get a simulation that basically looks identical, but it can calculate anywhere from 5 to 10 to 1,000 times faster, depending on the complexity of your hero or high-res geometry. And so another kind of more basic example of this is in here I just have a bunch of NURBS heads that are just falling with gravity. And so we can see they fall and they bounce, and the performance that I'm getting is quite good. It's close to real time, but each one of these heads, if I turn on wireframe on shaded, you'll see it has, a lot of vertices and a lot of points that would be considered for the dynamics. So I did the same thing in this scene as I did with the staff, where if I open the outliner, you can see I have my high-res heads, but each one has a point constraint and an orient constraint node. And then if I go and hide the high-res heads, and then display the low-res heads, so display show selection, what I'll be able to see is what the low-res heads look like, just a simple poly object that matches the approximation or matches the basic shape of my high res. And so that's what the simulation is actually being calculated on. So this is really a very good idea as far as workflow when you're setting up different types of situations. So the next thing that we're going to want to talk about on these rigid bodies, aside from our stand-ins that we have in here, is we're going to move on to the next attribute that we have on our rigid bodies, which is the active attribute. These objects in here are all active rigid bodies as far as all of these heads that are falling down. And then this ground plane is a passive rigid body. But you will see that any one of these objects actually has an attribute called active. And if it's on, it's an active rigid body. While for the ground plane, we'll see that active says off. So that if I select the ground plane and put active to on by entering a value of 1, if I hit play, what we're going to see is this, that those heads, when they hit the ground plane, actually push the ground down. Well, something that you can do is you can keyframe something from being passive to being active and vice versa. So that if I set up something where, let's say I had, I'm going to go and open, let's say, that example where we had, I'm just going to jump out here and grab that correct project. So I'm going to grab my scenes directory, and let's grab the one where we had, let's say, this. Let's use just the cylinder going down the stairs. We don't have anything going on quite yet in the scene, and so if I select the ground, we can see that there's already a couple rigid body nodes in here, which I will delete. Well, I'm going to select the ground and the stairs and turn them into passive rigid bodies. Select the cylinder and turn it into an active rigid body, so that if I connected gravity to it, we can see how it falls. Well, something that we saw was a way to select that cylinder and give it an initial velocity to determine what direction it moves in. But what I could also do is make it a passive rigid body by taking the active attribute and entering a value of 0. Now when I hit play, whenever something is a passive rigid body, it ignores fields. It'll only behave either by having manual keys on it, or you could use expressions or motion paths or whatnot. So let's say I go and I take that object and I set a keyframe at frame 1, and then another keyframe maybe at frame 20. If I hit play, what we'll see is that you can apply manual keyframes to passive rigid bodies. So whenever something's passive, it can be manually keyed. Well, if you go in on this object and at frame 1 keyframe its active state, and then I go to frame 10 and keyframe it from being passive to being active, so now I'm going to keyframe that attribute again. If I now hit play, we will see this. We will see that for the first 10 frames, it moves with my manual keyframes as a passive rigid body, and then from frame 10, it's an active rigid body. And also, the very important thing to notice is that when you switch something from being passive to being active, it will inherit the velocity that it had based on the manual keyframes. And so this is a very, very useful way to do a wide variety of effects. So if you needed to, for example, do something where I have, let's say, this situation where I have a character that I want to throw something. And so if I open up this scene, what we're going to see is I have this low-res version of a character that's holding this knife. And if I hit play, we'll see he just does this little motion to throw the knife. But the knife actually does not get thrown. What you can do is take that knife and turn it into a passive rigid body. But when we get to, let's say, frame 62, when his hand releases it, you can see when his finger is open, we can then go and switch that knife from being a passive rigid body to being active. So even if it's in a hierarchy, it'll work correctly if it's passive. So you'll notice that right now this knife that I have is parented into the hierarchy, but I have not set up any dynamics yet. Well, what I'm going to do is I'm going to also go and import those boxes that we had before so that he throws that knife at those crates. And so the first thing I'm going to need to do is take these crates and turn them into active rigid bodies. So I'll select the crate and say create active rigid body. Then I'll select the ground, create passive rigid body. And then what I'll notice in here with the ground actually is that it already was a passive rigid body. Then I will select the crates and connect gravity to them. So that now when I hit play, we will see those crates settle. Then I need to set up the knife. Well, right now this knife does not have any dynamics set up on it. It's just a parented object. So that basically if I select that knife, if we look in the hypergraph, what we will see is that this knife just has basically the hilt and the blade, which are grouped together. Well, to turn that into a rigid body, what we're going to want to do is first make sure you do not have any construction history on it. I will then select that group node, and before I turn it into a rigid body, I'm going to actually group it to itself, which is an important step. Once I've grouped it to itself, I can then turn it into a passive rigid body. So create passive rigid body. Since it's passive right now, it's going to still behave the same and just move with the hierarchy. But what I'm then going to do is at frame 1, I will keyframe its active state so that its active is set to off, meaning it's passive. But then I will go and scrub through until we get to the frame that the hand is supposed to let go, which in here is basically about frame 61. So I will now go to active, turn it on, and set a key. And if I now hit play, and I'm also going to connect that knife to gravity, so I'll go to the Dynamic Relationships Editor and select that knife and select gravity. And then let's hit play. And what we're going to see is this. And we can see the knife leaves the hand and then hits the crate. So you can see how easy it was to set that up by just making sure we do things in the right order, meaning that the hilt and the blade were grouped together, they are already parented into the hierarchy, then I group them to themselves again and turn them into passive rigid bodies. And now we can see if we look at it from a different angle, how they're behaving. And right now the knife and the crates have the same mass, and so the knife is actually pushing that top crate quite a bit. And so, again, this is showing the power of dynamics and using these simulations to go in and be able to create things that the keyframe by hand would be time consuming and actually aren't necessary due to this engine. So that's the active passive thing as far as keyframing between the states. And instead of actually setting the keys manually as far as going from passive to active, you will notice that you can select a rigid body, and under the rigid body pull down menu, you have set active key and set passive key. So you can choose to use those, but instead of using those, I tend to just keyframe it manually in the channel box. So the next thing that we want to look at then is if we select a rigid body, underneath the active attribute is an attribute called particle collision. I'm going to open a different scene for that. And for this scene, what we're going to see is that if I look at these gears, if I hit play, we can see that the particles can actually get these rigid bodies to be moved. And so it's actually the particles. I can go and move this emitter around, and maybe I rotate the emitter down. And when those particles hit the rigid bodies, you can see that they're actually starting to spin due to that collision. And so that is what the particle collision attribute on a rigid body node is for. So if I go in here and actually take this apart, so I'm just going to delete all of the rigid body elements that I have in here, as well as some other nodes that these rigid bodies have. And I'm just going to literally just sort of take everything apart and then put it back together again. And at this point, what we will see is this. So I have two pieces of geometry. They're not rigid bodies anymore, but I do have the particles, and those particles are not colliding with those two gears. So to set this up, when you want particles to collide with geometry, they don't have to be rigid bodies. I can just go in and select that surface and go to the particles pull down and say make collide. And then I'll have control over resilience and friction, resilience being bounciness and friction being friction. So I'll just go and apply that to both of those gears. But they are not rigid bodies. And if I then go into the dynamic relationships editor and select the particle object and go to collisions, we will see both of those surfaces. So if I select both of them, if I now hit play, what we will see is that those particles are colliding with and bouncing off those surfaces. And so if I went in here and selected that surface right there and went to its geoconnector node and increased the resilience, we will see that it'll be a lot more bouncy. And now those particles are bouncing off that surface in a more dramatic way. And so I'm just going to lower that resilience down. But in order to get those gears to actually move or rotate with the particles, I need to turn them into rigid bodies. So I will select each of them and turn them into active rigid bodies. And then at this point, if I hit play, they're still not going to be colliding or being pushed by the particles. All I need to do is select the rigid body now and go to the particle collision attribute and turn it on. And if I turn it on for both of those gears and hit play, what we will see is this. We can see that those particles clearly pushed both of those gears out of their way. And the way that I actually got them to then spin and stay put was to just use something we'll talk about in more detail later, which is dynamic constraints. I'm just going to add a hinge constraint to each one of these gears. And then the hinge basically locks the translation or position of the gear while constraining the rotation to only being able to move on one axis. And now when I hit play, we can see what we're getting as far as how those gears are spinning around while being affected by the collision of the particles. So if we just get rid of that gear on the bottom and hit play with just the single one, we can see how it's spinning due to the particle collision. So that's the particle collision attribute. The next thing in here is lock center of mass, which we've talked about before. And then we have a couple attributes, one called ignore and then one called collisions. The ignore attribute is off by default. If you turn it on, it means that the rigid body will ignore collisions and fields. And so at this point, let's say I went and just made a new scene. And in this scene, I went and actually we'll just go and open up these boxes and give them a ground plane to collide with. And so I'll just create a plane, scale that up, and place that underneath the crates. And then I will select that and make it a passive rigid body. And then select the crates, make them active rigid bodies, and connect them to gravity. We will see that they will fall and then collide with the ground. If I select all of those crates and turn ignore on, so give it a value of 1, so ignore is on, we will see that those rigid bodies do not fall with gravity and they don't collide. If I turn ignore back off, they'll go back to the default behavior, and then underneath ignore you have collisions, which is on. If I turn collisions off, as you'd expect, they will fall with gravity, but they will not collide with each other. So ignore, if you turn that on, will ignore fields and collisions, while collisions, if you turn that on, it'll just ignore collisions, but will still behave with fields. So that at this point we can see that collisions are off. And so let's turn collisions on, and now we're getting this behavior again. The last attribute that we will see in the channel box is an attribute called apply force at. And a good example of that is just this sort of a simple one where I have this sphere and I have an air field. This sphere is an active rigid body. The center of mass for that sphere is at the center of the sphere. I also then have an air field, and we can see this air field right here. I've actually parented the air field to a cone so it's easier to see what direction the air field is blowing wind in. And that air field has a spread, like a spotlight, turned on. So if I hit play, notice how that air field is hitting the sphere at the bottom of the sphere and causing the sphere to spin, meaning the air field is creating torque, or a sort of a spinning motion on that rigid body. Well, if you select the rigid body and you go to the apply force at attribute, by default that attribute is set to bounding box. But there's 3 settings that you can use: center of mass, bounding box, or vertices. If you choose center of mass, you are basically turning off torque, in the sense that if I hit play now, nothing happens because the center of mass of this sphere is not within the spread of that airfield. So that I'd have to actually raise my airfield so that the center of mass is within its spread, so that when I hit play, we can see that the sphere gets pushed by that airfield, but it does not start to spin. And so that's what's going to happen if the force is only being applied to the sphere based on a single point. But when you select the sphere and set it to the default attribute of bounding box, it then applies the field to the 4 corners or the 8 corners of the bounding box of that surface. And so in this case, you also might not get accurate results. So you'll notice when I raise the airfield to here, it's working. When I raise it up a little bit more, it's not, because one of the corners of the bounding box of that sphere are not within the spread, even though the vertices are. And so what you'll often find yourself having to do to get the most accurate results is change the default setting of bounding box to vertices, so that apply force at is set to vertices or CVs, which is the 3rd option. And now when I hit play, we'll see that it's working. And also we are getting correct torque. So if I move the airfield up here, it's going to spin from the top. If I move the airfield down here, it's going to start to spin from the bottom, as you would expect based on how that piece of geometry is being hit. So that covers pretty much all of the attributes that you will see in the channel box. But there is one more attribute that is very important for rigid bodies that you will only see in the channel box, or in the attribute editor rather. If you select the rigid body and go to the attribute editor, you will see the rigid body node listed in there. And if you select the rigid body node, there is a folder called performance attributes. And if you open that up, there is an attribute in here called tessellation factor. For a poly object, that does not make a difference, but for a NURBS object, it makes a very big difference. And what I'm going to do is I'm going to create something quickly where I just, let's say, have a curve, and then what I'm going to do is extrude a circle along that curve to make a NURBS object. And so I'm going to go in and take the circle, take the curve. In modeling mode, I'm going to do an extrude. And let me change the options for extrude so that it extrudes a tube. And then I'm going to go in and delete my curves so that I just have this NURBS piece of geometry. And what I want to do is then create a sphere and get that sphere to fall with gravity, but then enter the tube and roll out the bottom of the tube. So the sphere will be in dynamics mode. I will delete history for both of them, turn the sphere into an active rigid body, turn the tube into a passive rigid body. Well, the first thing you know that you need to check for the NURBS object are the normals. And if I go to display NURBS components and turn the normals on, notice that for the tube, the normals are actually by default pointing in, which is what I need. Because if the normals were pointing out, then we will get an error. So the normals are correct right now. If I then take that sphere and apply gravity to it, and let's turn off or hide the normals, when I hit play, and I'm going to go into an orthographic view, we will see that it does go and enter the tube, but we're getting collisions that don't actually make sense, in the sense that it's entering the tube, but notice that it seems to be colliding with the tube where it's not actually touching the edge of the tube. That's because this NURBS object is being tessellated into polygons to determine the collision model. And so what you need to do is select the NURBS object, go to the attribute editor, go to its rigid body node, open the performance attributes folder, and increase the tessellation factor. The default is 200. If I enter a value of 2000, what we're going to see when we go back into the front window and play back the simulation is we are now going to get a more accurate result. It'll be a little bit slower, but you'll notice that the result what we're getting is more along the lines of what we were expecting as far as how that ball is entering and exiting that tube. And so something that can give you another idea of how this is working is if you select that NURBS object and go to Modify, Convert NURBS to Polygons, if you just set the tessellation method to count and enter the value of 200 and hit Apply, you would see what poly object you're going to get and how rough that looks compared to your actual original tube. But if I select that tube and enter a count of 2000 and hit Apply, we're going to get a much denser poly object. And so that's going to more accurately represent the NURBS object for the dynamics. So at this point, we've covered all of the main attributes of the rigid body node. And so the next thing we're going to want to talk about is the rigid body solver, which is basically what controls how the engine behaves in general for your scene. When you go to the solvers pull-down menu in dynamics mode, you will see that you have something called rigid body solver, and then it says current rigid solver and create rigid body solver. Whenever in your scene you turn something into a rigid body, it'll automatically create a rigid body solver node. And so we can see that we have a current rigid solver in the scene, which is highlighted or checked right here. You can create multiple rigid body solvers, but only one will be active at a time, so that you could have different solvers with different settings and performance settings, so that maybe one is less accurate but faster than another, and you toggle between them based on what you're doing. If I go to the rigid body solver, there are several attributes in here that need to be discussed, but again, we're going to try and go through this kind of quickly so that we have a lot of time to talk about the constraints. So with the rigid solver node, what we're going to see is that we have, if we look and close everything up, we have a few folders. The first folder that you will see in here is called rigid solver attributes. And the first two attributes that we will see in here are step size and collision tolerance. Step size is how often Maya looks for a collision, and that's how often in a fraction of a second. The default value in there is 0.03, which means that Maya is looking for collisions every 0.03 seconds. And so if you have a situation where you have objects that are moving very, very quickly, you may need to lower that number, because if an object is moving very fast, so that between two moments in time where Maya is looking for a collision, it actually passes through an object or maybe gets halfway through an object. The next time Maya looks for a collision, if those objects have already passed through or are halfway through, you're not going to get an accurate simulation. So basically just remember, if your dynamic simulation stops because all of a sudden objects go through each other, if assuming those objects are not single-sided and they actually have a thickness to them, then you would have to go into your rigid solver and just lower the step size. Then you have collision tolerance. Collision tolerance is the distance in units between which two objects are considered to be colliding. So the default value for that is very small. It has an value of 0.02, which means that when two rigid bodies are 0.02 units away from each other, they will collide and then bounce off each other. So if you have a scene where your objects are very, very small, you may need to lower that value. Otherwise, those objects may appear to bounce off each other before they actually are visually touching. The next attribute that we have in here is called scale velocity. This is purely visual. Something that we will see is if I go to a folder called Rigid Solver Display Options. By default, you'll see that there are four things in there, and it says Display Constraint and Display Center of Mass, which are both on, and then Display Velocity and Display Label are off. These are relatively straightforward. They're purely visual. They don't change performance. So display center of mass causes that little X right there to be visible. If I uncheck it, you'll see the X will disappear. If I turn on display label, you will see that it now says active right here, and that it says passive for this passive rigid body. So it's actually giving us visual labels for these objects in the scene. If I turn on display velocity, what will happen is when I hit play, notice that for my sphere, there is now a little arrow beneath it pointing down. It's purely visual. It's just telling you what direction that sphere is moving in, so that when you pause your playback, you can look at the objects in your scene and know what direction each object is moving in. Well, if you go to the scale velocity attribute up here and you increase it, let's say to a value of 5, it will not make your objects move faster. All it will do is make that arrow longer. Because if you have objects moving very, very slowly, it might be difficult to tell what direction they're moving in. And so here we can see how that arrow is changing as that object changes direction, as it bounces off of our collision object. So that is what display velocity is for, and then the scale velocity. So if I open, let's say, a different scene in here, I'm going to go now and open a scene where what we're going to do is basically get this sphere to hit this object and cause it to shatter. Well, what I've done is I selected this polyplane, selected specifically one of its vertices, and so you can see if you select a vertex of a polyplane, you can go to the effect which is called Create Shatter, and if I choose, let's say, a crack shatter and hit apply, what it's going to do is actually break that poly object into separate pieces. And so I've chosen the crack shatter where it's actually going to extrude some shards, and so we can see I'm going to have separate pieces. And if you needed to do an explosion where an object is breaking apart, the shatter effect can be very useful. And so in this scene, I've already done that, so you can see I've got this plane, but then right behind it, you can see I have some shards that were made by the shatter effect. One thing that I have done with these shards, though, is I have moved them a little bit so that they're not touching. Because you have to be very careful whenever you use the shatter effect. The shards that it creates are on top of each other, which will give you error messages if you turn them into rigid bodies. And so it's important that you just move them so that they are separated and not intersecting. And so the way I'm going to get this object to look like it's shattering is basically, you can see that I already have some motion on this sphere. And this sphere is already an active rigid body with an initial velocity. But what I basically want to do is when that sphere hits this plane, I want that plane to shatter. So you'll tend to do that by basically having your high-res piece of geometry, whether it's a tank that's being blown up or a building or whatever. And then once this object hits it, you will keyframe the visibility off of your high-res object and then keyframe the visibility on of all of your shards, which are then going to be active rigid bodies that are going to be affected. And you also at that point could keyframe those objects from being passive to being active rigid bodies. So in here what I'm going to do is I'm going to go and figure out exactly at what frame the sphere is hitting that plane. So I'm just going to step forward one frame at a time, and I can see that it's at frame 16. So what I'm going to do is select my plane and then keyframe its visibility on at frame 1 and then off at frame 16. So let me just move forward to frame 16 and set that key. So that now when I hit play, we see this. The moment the sphere hits that plane, the plane becomes invisible and we can see the shards that were behind it. Then what I'm going to do is simply select each of those shards that are back there, and then at frame 1, I'm going to turn them into active rigid bodies. And now when I hit play, automatically we will see this. And so it's actually a relatively straightforward effect to do using the right workflow. And so we just keyframe the visibility and then just had some rigid bodies in here. So when we're looking at this, that is playing back, we can see that our simulation begins at frame 1. Well, if we go back to the rigid body solver, we can see that we have an attribute in here called start time, which has a default value of 1. If I enter a value of, let's say, 50 in there, what that will mean is no dynamics will become calculated until frame 50. So that if I hit play, we will see that the visibility on my object still changed at frame 16. But aside from that, if I hit play, notice that that sphere does not start moving until frame 50. And so in here, go and escape here for a second, you can see what the start time is doing. You are changing when your simulation is beginning. And so let's actually go in here and for a second open a different scene. Well, actually, no, we'll keep working with this scene. We'll go back to our rigid body solver and set the start time back to frame 1. Okay, and hit play. Underneath the start time, we then have an attribute called current time. And for this, actually, it'll be easier to show if we just work on a simpler scene. So let me just make a new scene. And I'm going to create, let's say, objects that are falling. So again, I'll just go and grab these crates. I will turn them all into active rigid bodies. I will connect gravity to them. And then I will create a plane, or a ground plane. I'm going to move this below them. And then I'm going to turn that into a passive rigid body and hit play. So that if I went to my rigid body solver and set my start time, let's say to frame -50, and set my time slider to start at frame -50, you'll see that my simulation will actually begin earlier. So that by the time I get to frame 1, maybe I can have my objects already settled in the position I need my animation to begin with. But aside from using the start time, let's get that back to a value of 1, we then have our current time attribute. The current time attribute is something that is connected to your time node. And if you open up the outliner, you will see if you turn off display DAG objects only, there's a node in here called time. And if you go to the attribute editor, you'll see that it has a value of 1. Well, if I go to frame, let's say 30, it now has a value of 30. So this just stores what frame we're at. And this node is connected to your rigid body solver. Well, you can actually disconnect them by right-clicking on the current time in your rigid solver and going to break connection. So that if I now go back and hit play, nothing happens. Well, what you can do is you can manually keyframe the current time. If I keyframe it with a value of 1 at frame 1, then I go to frame, let's say, 210, and give it a value of 210, and set a key. If I hit play, we will see we are getting our regular result. But what I could actually do is not keyframe it in such a straightforward way. Because if somebody tells you that they like the simulation that you've done, but you need to speed it up a little bit or slow it down, it's going to be hard to do that by just modifying or tweaking your fields or changing the mass on your objects or whatever. So what you can do is instead of trying to tweak a bazillion different things, you can just go and keyframe your current time. So that instead of it having the keys that I set, I'm just going to select the rigid solver node by hitting the select button. I'm going to delete that key I set at frame 210. I still have my keyframe at frame 1 where the current time is set to 1. But then what I'm going to do is go to frame 100, and instead of entering a value of 100, let's say we enter a value of 20 and hit a key. If I hit play, you're going to see that they're going to move really slowly for that first 100 frames. Because basically in 100 frames on our time slider, they are only moving through 20 frames of the simulation. What I can then do is go to frames, let's say 150, and enter a value of 150. What's going to happen then is they're going to start by going really slow, but then once we get to frame 100, they're going to speed up. And then I could go to frame 210 and enter a value maybe of something like frame 160 and hit a key. So that now what happens is the simulation will start off slow, speed up at frame 100, and then slow down again at frame 150. So you can do kind of like matrix type stuff or whatever where you need things to maybe start off at a certain speed and then slow down or then speed up, which is actually a pretty common effect to see where something's exploding in real time and then all of a sudden goes and moves into slow-mo, whatever. That's something that you can do by modifying or keyframing your current time. Then underneath that, we will see that we have rigid solver methods. Basically, the only thing to know about that is you've got 3 options where the default, which is Runge Kutta Adaptive, is going to be the slowest, but it's the most accurate. Then you have Runge Kutta, which is going to be less accurate but faster, and then Midpoint, which is even faster and even less accurate. So you'll always use Runge Kutta when you're really trying to get your simulation to behave correctly. But once you're happy with your simulation, you could always switch it to midpoint so that things calculate a little bit faster, even though they're going to be a little bit less accurate as far as the collision. Then the next folder that we will see in here is called Rigid Solver States. What I'm going to do in here is I'm going to delete the animation that I put on current time, and then I'm going to reconnect the time node to my rigid solver. To do that, I just need to select the rigid solver, open up the connection editor, load the rigid solver as my input, and then select the time node in the outliner. And once that's selected, I will load that as my output. Then I will take the out time from the time node and connect that to the current time on my rigid solver, so that if I now go back and hit play, things are back to normal. What I can then go and do in here is going to my rigid solver. If I open up the rigid solver states, we can see that we have some checkboxes. What these do is you'll see that the first 4 you will rarely change. The first one, which is called state, if you uncheck that, will just turn off all dynamics. So I'm going to turn state back on. Then you have friction. If you turn that off, it's just going to turn friction off for your scene, but you'll still have bounciness. So you can see these boxes are just sliding around because there's no friction. If I turn friction on but turn bounciness off, we will see that no bounciness will occur. Then you have something called contact motion, which if I turn that off, you'll see it has turned off friction and bounciness. So you're going to tend to leave state, friction, bounciness, and contact motion on, which is the default. But then you have an attribute called contact data. If you turn that on, what that will do is for each rigid body in your scene, it will allow you to query some read-only attributes. So these attributes on your rigid bodies are only turned on when you turn on contact data. And you get 3 attributes. You get contact position, contact count, and contact name. So that you can basically, in an expression, query how many times the collision has occurred for a specific rigid body. You can also query where in the scene the collision occurred and the names of all the objects involved in the collision. And so for an example of an expression you might write is, let's say every time a collision happens, you want a light to turn on. For something like that, you would write an expression that looks kind of like this expression I have here in Notepad, where you would say, if rigidbody1.contact count, so this is one of those attributes that are enabled when you turn on contact data. So if rigidbody1.contact data or contact count is greater than 0, then some point light's intensity equals 5. Else, the point light's intensity equals 0. So what this is basically saying is that if this rigid body 1, has collided with anything at the current frame, so if the contact count is greater than 0, the light turns on. Else, the light turns off. So an example of the obvious usefulness of going to your rigid body solver and turning on contact data. But it does slow things down a little bit because it then needs to store all of that information. The next checkbox you get in the rigid solver is called Allow Disconnection. You will pretty much never use that. What that will allow you to do is manually disconnect the rigid body node from the transform node of your geometry. And whenever you're trying to delete rigid bodies, the way you really want to do it is the way I've been doing it, where you just go in to the outliner, open up your objects, and then just delete the rigid body node manually by just selecting it and deleting it. And so this way we'll see that for those cubes, they're not rigid bodies anymore. Okay. Going back a few steps to before I did that, so that my objects are falling again. So now they're all falling with gravity. If we go to the rigid body solver, the last thing in here that we want to talk about is something which is, again, under the rigid solver states folder, which is called cache data. That allows you to cache things into memory so that your playback can be faster and so that you can scrub. Because as we've seen, if I try and scrub through my playback right now, I can hit play, but when I scrub, you'll see that we get an unpredictable result, and it's not actually playing back right now at all. All you need to do to use a cache is go to your solvers, rigid body solver, and turn on cache data. Then if I go back to frame 1 and hit play, we will see that it'll play through it, but then if I stop, I can now scrub. So you can see that as I scrub in my time slider, it is now using the cache from memory. But if you make any changes to the fields in your scene or the mass on your rigid bodies or anything, you will need to make sure that you delete the cache before you hit play again. Because whenever you have a cache in memory, it will only use the cache and will not recognize any changes you make to your scene. So you will see that if you go to the rigid solver node, that there underneath the cache data checkbox is a button that says delete cache. And you can just press that button if you've made a change to a field or something. And so otherwise, you could just go and turn off the cache completely by unchecking it. And now you will see it'll just go back to its regular performance and I can't scrub anymore. Another thing that's useful is instead of caching, let's say that you know that you are now 100% done with the simulation that you have been working on. And now you want to maybe incorporate some character animation into the scene. Well, the thing is that since you cannot have your playback speed set to normal or set to real time, meaning that in our animation preferences, our playback speed is set to play every frame, if you're trying to incorporate some character animation, it can be a little bit frustrating because when you're animating a character, it's very nice to be able to work at real time. What you would do for a situation like that is once you're done with your simulation, which maybe is set up in a different scene, you might then bake the simulation into keyframes so that you can then not have to worry about the Dynamics engine. So basically, the way that you can bake Dynamics animation into keyframes is you simply select the objects. So in this case, I'll select all these crates, select the objects that you want to bake, and then just go to Edit, Keys, Bake Simulation. And if you go to the options for that, this Bake Simulation tool is used to bake dynamics, or rigid body dynamics, as well as inverse kinematics. So some of the options in here we don't need, and it also can bake some other things in Maya as well. So not all of the options in here pertain to rigid body dynamics. But you'll see that the first option here is hierarchy, selected or below. So I have selected several crates, and so I'm just going to use hierarchy selected. Channels, all keyable. Then driven channels, control points, and shapes don't matter. They don't really have to do with these crates right now, because these crates don't have any set-driven key channels, and their shapes are not being animated. Then it asks you the time range that you want to bake. You can either use your time slider or enter a start-end range. My time slider down here goes from frame 1 to frame 210, and so I'll just choose time slider. Then underneath that, it asks how you want to sample your dynamics, and the default value is sample by 1, which means that it's going to create a keyframe at every frame for each one of those crates, and that's the setting that you want, so that you get keyframes that perfectly match the dynamic simulation that you had. You can always go and simplify those curves later in the graph editor, but for now you want to make sure you sample them by 1. Then the 3 checkboxes we see underneath that, keep unbaked keys, sparse curve bake, and disable implicit control, we also don't need to worry about with these rigid bodies. And so what I'm going to do is just with these options, I'll hit bake. It's going to run through your simulation once, and then once it's finished running through the simulation, we will see the keyframes appear for all these different objects. And so now, what we will see is if we select any of these crates, notice that there's a whole bunch of keyframes in the time slider. And if I go to the graph editor for one of these, so I'm just going to jump into the graph editor, you will notice that we have some very, very heavy curves because there is a key at every frame. But the thing that we can do now is notice that if we hit play, it's going to play back faster. And then also, if I went into my outliner and let's say deleted my gravity field, notice that they still are falling because it's not using that field anymore. It's actually using keyframes. So if I went into these rigid bodies and actually deleted the rigid body nodes so that the rigid body nodes themselves are gone, if I hit play, we are still getting the simulation. So all of the dynamics are gone from the scene. I've deleted the rigid body nodes, I've deleted the fields, and so that I can now go into my animation preferences and set my playback speed to real time. So that if I now go and hit play, we're actually seeing this with our correct timing. And so baking your keys is very, very handy. Also, you can use it when you want to copy animation from one object to another, meaning that you might use dynamics to get one piece of debris flying away from an object and spinning around, then bake that into keyframes on that piece of debris, and then maybe copy the animation curves from that one piece of debris to a bunch of other ones. Instead of calculating dynamics on thousands of objects, you could just maybe calculate it on 50 and then copy those keys randomly amongst different objects in your scene. So now that we've talked about baking keys, we've talked about the rigid body solver. So let's check a couple things. Rigid body solver has been talked about. We've talked about all the attributes on rigid bodies, baking keys. So now we can really start talking about the other things we can do with rigid bodies, which specifically is going to be rigid body constraints. And so we've already seen an example of rigid body constraints when I started off with the catapult that was open. And so if we just get that scene back, and let me just get this loaded. By default for this scene, it does not have a cache. And so if I hit play, it's going to play, but notice that since my playback speed is set to real time, I'm going to have to hit escape because it's playing really jerky. So I'm going to go to my animation preferences, put my playback speed to play every frame, and now we can see it's going to play back, albeit not very fast. It's playing at about 8 frames per second right now. But if I go back to frame 1, go to my rigid body solver, go to the rigid solver states folder, and turn on cache data. Then I will go in here, hit play, and then it's going to cache this into memory so that we'll be able to play back faster. So we're going to let it cache a few frames. We can see we've got a bunch of things that should make sense now as far as how these are working with the active and passive rigid bodies in the scene. So let's give it a few frames to play back. Maybe it's going to play until frame 200. Then I'll change my playback range to 200 frames. And next time I hit play, look how much faster it is. It's now playing at 25 frames per second because it's playing from memory using the cache. And then if I go in here, we can see that I can now scrub because that cache is being used. So now let's begin talking about constraints. So with constraints in Maya, the first thing we're going to look at is something called the nail constraint. And if I hit play, what we're going to see in this scene is we have a basic pendulum. And what we're looking at is actually 5 rigid bodies. Each one of these spheres is an active rigid body. Then they are constrained via nail constraints to create the motion that we are looking at. And so let me just delete the animation that I have on this camera so that if I hit play, we can take a look at what's going on. So basically these lines that we're seeing on these spheres are nail constraints, where we have more than one constraint applied to each one of those balls or each one of those spheres. There are several different types of constraints in Maya, and if you select a rigid body and you go to the rigid body pull-down menu, you will see an option called Create Constraint. And if you go to the dialog box for that, you will see at the top where it says Constraint Type that there are 5 different types of constraints: nail, pin, hinge, spring, and barrier. So the first thing we're going to talk about is a nail constraint. And before we see how this pendulum is set up, if I just create something simple, let's say I just create a sphere, and we'll move the sphere off to the side. With this sphere, what I'm going to do is create a constraint on it. So first I'm going to turn it into an active rigid body. Actually, first I'm going to delete history, then turn it into an active rigid body. Then I'm going to go to Create Constraint, and in the options I'll choose Nail. There are no options to set, everything's grayed out. I'll hit Create. And what we will see is if we look in the outliner, that here is my sphere, and then there is a new node in the scene called Rigid Nail Constraint. Constraints are their own node. They have their own transform nodes. And so you can see that I can select the constraint and move it. By default, this constraint for the nail, you'll see will look like a line. And basically you will have a line that will be drawn from the pivot of the constraint to the center of mass on my sphere. So I can select my sphere, go to the center of mass Y in the channel box, and by moving the center of mass in Y, I can change where that constraint will calculate from as it's moving the rigid body. So at this point, if I want to see what this nail constraint does, basically I could just take this sphere, connect, let's say, a vortex field to it, and then for that vortex field, I'm just going to position that vortex field so that its axis is kind of where that nail is, and I'll hit play. And then we're going to see this. So notice that that sphere is going to start spinning around, but the thing is that it's locked to that nail constraint. And so these constraints allow you to basically mimic mechanisms that you will see in the real world without actually having to try and recreate them completely using dynamics and whatnot. And so it's just going to speed things up. Also, let's say I get rid of the vortex field and I just apply gravity to that sphere, and then I take that sphere and maybe move it a little bit, rotate it a little bit, and hit play. We're going to get this. Then let's say I grab that nail constraint and set a keyframe on it. You actually can keyframe the movement of a nail constraint. So if I set a key on its translation and then I move it, while I move it, it's not going to pull the sphere because dynamics don't calculate in real time. But if I move it over here and then set a keyframe, let's say at frame 50, when I hit play, we will see this. You can see that as that nail constraint is moving, that it is causing the appropriate movement on that sphere. And that nail constraint could also be parented to something. And so if we try and look at how something like this pendulum is set up, if we wanted to recreate it, all I'd need to do in here is I'll go and delete all of the constraints that are in the scene. And let me also just delete these pieces of geometry that are in there. And so now what I have is just the spheres, 5 active rigid bodies, which have their center of mass positioned to the top of each sphere. If I hit play, we'll notice that they're just going to fall with gravity because they already have a gravity field connected to them. Also notice that the sphere that's on the end, this one right here, has an initial velocity in the x direction, which is getting it just to move in x. Well, what I can do is select one of these spheres and just create a nail constraint on it. So I can just hit apply and then move that nail constraint up a little bit and maybe move it to the side. Then select it again and hit apply one more time. Now I have 2 nail constraints on that sphere. So if I do that to each of these spheres, giving each of them 2 nail constraints, and then once I create the nail constraints for each one of these spheres, all I'll need to do is position those nail constraints so that they all kind of are making sense with the way things are modeled in this scene. So let me just go and apply that. Now I'm just going to go to the side view, take a look at all these constraints, and then I'll just grid snap them, and then grab these and grid snap those. Then I will move these up to that bar, move these to this bar, so that now we can see this in the scene if I select all of those constraints. And that's it. If I now hit play, you can see how easy it is to create something like a pendulum by just creating multiple nail constraints on these spheres. And so as far as actually having a piece of geometry that looks like a piece of string, I just created a cylinder that had its pivot point at the location up here where the nail constraint is, and then I aim constrained it to be aiming to the pivot of the sphere, which is at the top of the sphere. And that way the string looks like it's moving with the actual nail. The next constraint that we want to talk about is the pin constraint. For this, I'm going to create a new scene. And a pin constraint is basically a way of connecting 2 rigid bodies with a ball joint. So that if I create something where, let's say I'm going to create a polycube, and for this polycube, I'm just going to scale it a little bit. And let me just turn on wireframe on shaded. So with this polycube, I'm actually going to make some copies so that I've got a few of them. And these, instead of being cubes, these could be train cars. Or these could be, let's say, chain links, where each one of these are actually, rotated like this to represent a chain that you're trying to recreate. What I can do is I'm going to turn these 4 into active rigid bodies and turn this one on the end into a passive rigid body. I'm going to take the one on the left and apply gravity to it. Then the one on the right, since it's a passive rigid body, I'm going to set a couple regular keyframes on it. So I'm just going to go in and set some keys so that if I now hit play, we're going to see this. We can see that, and let me change my playback range. We can see that the block on the left is falling with gravity, while the block on the right is just moving with the manual keys that I set. Well, I can now can connect each of these rigid bodies to the one next to it using dynamic constraints. So all I need to do is select this one and this one. This one's passive and this one's active in this case, and go to create constraint, and I will choose pin. There again are no options, everything's grayed out, and if I hit apply, what we will see is in the outliner, we have a new node, which is called our pin constraint. And by default, it positions itself at the center between these two objects with a line drawn from the location of the pin to the center of mass. Then I will select these two and create another one. These two, create another one. And these two, create another one. And at this point, if I hit play, there you go. So you can automatically see the behavior that we're getting very intuitively just by using pin constraints. So basically each one of these blocks are connected with ball joints. And so if you needed to create, dynamic simulation on an actual skeleton of a character, you could actually use something like this and then constrain, the joints of your skeleton to these actual rigid bodies would be one way to go about something like that. But at the same time, you could see if you were creating something like a chain link, you can create results that will look almost 100% accurate, but calculate very, very quickly, as opposed to creating a chain where each link is actually colliding with each other perfectly and accurately. Because if you did it that way, it would be kind of slow. This is kind of a shortcut to doing something like that. So another example of using a pin constraint would be doing something like this earring example, where if you wanted to give a character earrings or let's say elements that are hanging from whether it's a necklace to bracelets to whatever. In this case, what I've done is I've taken a region of a patch model of a head that's already been skinned. And so this is just a head that I modeled with a bunch of patches. I deleted a bunch of them, so we're just looking at the ear region. And it's already skinned to a skeleton. So if I hit play, we're going to see that we're going to get some motion in here. And if I zoom in where the earring is, we can see that it's actually behaving dynamically and how it's moving around and so forth. Well, if I go and grab the head joint, we will see that if I rotate it, things are already skinned. The way the dynamics are set up is that basically for this very simplistic earring, this is a passive rigid body, and then these two are active rigid bodies. Each of these three objects are parented to the head joint. So that head joint, which is right there. Then I created a pin constraint between these two rigid bodies and another pin constraint between these two rigid bodies. And that's basically it. And then as a last step, if I hide my patches, I created this little collision piece of geometry. A simple poly object, which is a passive rigid body, which is also parented to the head joint, so that these two elements won't go through the geometry. So you can see how it's calculating a lot faster now that my patches are hidden. And you can see that it's behaving correctly. Because instead of using this, I could have turned these objects into collision objects, but it would have been a lot slower and it wouldn't have looked any more accurate. So another example of a pin constraint. The next constraint that we're going to look at is a hinge constraint. Hinge constraints can be used to do something like the gears we looked at earlier. So if I open this file, we can see that I just have some gears, which let me just delete some of the particles that are in the scene. And if I hit play, we can see that as these active rigid body spheres are falling with gravity, they are hitting these gears, which are then spinning around. Well, basically each one of these gears is an active rigid body, which has a hinge constraint. So if I went and made a new scene, what I'll do in here is I'm going to create a cube and a sphere. And then what I'm going to basically do is take that cube, scale it up a little bit, and let's say that this cube is supposed to be something like a door. I could then go in, turn both of these objects into active rigid bodies, and then give my sphere an initial velocity in the negative z direction, let's say of negative 20. So that when I now hit play, we get this. And we can see that that sphere is knocking that cube, and they both have the same mass right now. I'm going to give that door a greater mass, maybe a mass of 20, so that when I hit play, it's not quite as affected by the sphere. Well, what I can then do, if this was supposed to be a door that has a hinge, I can select that cube and just go to Create Constraint and choose Hinge. You will get options to set the orientation, but instead of setting it in the dialog box, I'm just going to hit Create. We will see in the outliner, our hinge constraint is a separate node. And if I go and look in, let's say, wireframe mode, it'll be positioned at the center of mass. but I can then move it as well as rotate it. So I'm going to rotate my hinge constraint 90 degrees, and then in the top view, I'm basically going to place it at the corner of my cube, where I want the hinge for that door to be. So that now, when I hit play, we get this. And if I went to that door and lowered the mass back to a lower value, let's say a value of 2, we can see how simple a hinge constraint is, but how effective it can be to creating this kind of simulation. You can also use a hinge constraint if you were actually doing something like train cars. Train cars are connected by a hinge constraint, not a pin constraint. And so that something like that could easily be done. So if I went and selected this object, instead of having a hinge constraint on a single rigid body, I could select this cube, maybe make some copies of it, and so now I have, let's say, 3 cubes, and then I could connect these cubes via hinge constraints. And so now I will have a hinge constraint between this rigid body and this rigid body, and between these two. So that if I again had a situation where I create that sphere, which is flying towards one of the objects, which is an active rigid body that has an initial velocity, when I hit play, we'll be able to see how they get pushed. Right now, it's hitting them, but you can see the way the hinge is oriented, it's not creating any rotation. But if I took those constraints and rotated them 90 degrees, so I'm going to rotate each one of these 90 degrees in X, and now I hit play, we see this. Because it's only able to rotate in just one axis. So that's basically the hinge constraint. The next constraint that we're going to want to look at is the barrier constraint. Barrier constraint is very, very simple. It basically is something used to limit where in your scene a rigid body can go. If I select, let's say, the sphere, and say create constraint barrier, and hit create, it'll be created at the center of mass, but I'm going to move it, and we get something that looks like a plane. If I rotate this plane, what we have is an infinite plane in the scene that will limit where that rigid body can move. So if I now hit play, we will see this. Notice that that sphere cannot move past the barrier constraint. It will not bounce off the barrier constraint because that barrier constraint does not have any friction settings or bounciness settings. It'll just basically hit it and slide. So if I moved that barrier constraint back a little bit, what we're going to see, or actually let's say, in this case, that sphere is bouncing off, but maybe I'll just go and take the sphere and move it this way a little bit. When I hit play, we can see when that sphere gets stopped, once it encounters the barrier. So it's just a simple way to limit where in your scene your rigid bodies can move. And then the final constraint that we have in Maya, which is very, very handy, is the spring constraint. So when I go to constraint type, we'll see spring, and then spring has its own folder in the creation dialog box. Now, spring constraints are something that I actually use to create that catapult, but before we look at that, if I just create a new scene, and in this scene what I'm going to do is, let's say we create a sphere, and I'm going to move this sphere so its position in Y is 10 units. And then with this polysphere, I'm going to delete history on it, and then I'm going to turn it into an active rigid body, and then I'm going to go and turn on wireframe on shaded and create a spring constraint. By default, this constraint, like the other ones, will be created at the center of mass. If I move my spring to the origin, we're going to see a line drawn, kind of like the nail constraint. But the difference is that a spring constraint will behave the way springs work in the real world. If you think of something like anything from a shock absorber on a car to a slinky or whatever, springs are objects that if you compress them, they will try and extend back to their default length or rest length. If you stretch them, they will snap back or spring back to their default length. So that's what these constraints do. So when you create a spring constraint on a single rigid body, its default rest length will be 0. And if you select a spring constraint and look in the channel box, you'll see that it has stiffness, damping, and rest length, as well as an on-off toggle for the constraint, which all constraints have. The rest length right now is set to a value of 0. let's say I set the rest length to a value of 10. Well, right now my sphere's position has a translate y of 10. Its center of mass is at the center of that sphere, and my spring constraint I positioned at the origin, which means it is 10 units long. So if it's 10 units long and the rest length is 10 or 10 units, if I hit play, nothing happens. But if I set the rest length in the channel box for my spring to 5 units and I hit play, we get this. Notice that that spring is trying to compress itself back down to its default rest length. If I set the rest length to a value of 20, and right now it has a length in here of 10 units, it's going to extend itself to get back to that rest length. So basically what we're seeing is springs are behaving relatively intuitively, but the next attributes you need to use to tweak them is stiffness and damping. Stiffness determines how quickly they get back to the rest length, while damping determines how quickly they lose energy. If I set the stiffness to a value of 50 and enter a rest length of 15, we will see this. Notice that it very quickly tries to stretch back to its rest length, but then it keeps bouncing, and it takes a very long time to slow down. That's when we can increase the spring damping. If I increase the damping from a default value of 0.1 to a value of 0.8 and hit play, we will see this. Notice how quickly it loses energy. If I enter a spring damping of 3 and hit play, it loses energy very fast. So let's say the rest length instead of 15 was 3 units and I hit play. If I go in here and set the rest length, let's say to a value of, 20 units, a damping of 0.8, and a stiffness of 100, and I hit play, you'll be able to get an idea of how you can control these constraints. So spring constraints can be created on single rigid bodies, but they also can be created between multiple rigid bodies. So that if I had 2 spheres, selected both of them, and created a spring constraint, by default the rest length for that new constraint will equal the distance between the center of mass of these 2 objects. Then if I selected one of them and gave it an initial velocity in the x direction of 10, what we will see is this. Notice that the one on the right has initial velocity, the one on the left doesn't. But because of the spring connecting them, when the one on the right moves, it pulls the one on the left. And so that's the basics of a spring constraint. So if we look at something, let's say like that catapult, the way I set up the catapult is basically, let me just go in and center my view, as far as how this is built, the catapult is rigged where we've got a piece of geometry here, meeting the arm, as well as another piece of geometry right here. I selected those 2 pieces of geometry and grouped them together. I then took that group node and turned it into an active rigid body. For that active rigid body that's been grouped, that is a group, I then added a hinge constraint, which I placed right here. Then I added a spring constraint, which I placed over here. So that spring constraint at frame 1 only looks like it's about 3 units long. But if I select it, we can see its rest length is 25 units. Which basically means that once I hit play, that spring is going to try to extend itself, get longer, but this rigid body currently has a hinge constraint which is going to limit its motion. Then I also have this object right here, which is a passive rigid body, which is going to block how far that catapult can move forward, and then this ball is an active rigid body. So with all of those things understood, let me just go and delete the animation that's on this camera. If we hit play, that should explain how this catapult functions. So that if I went in and took this passive rigid body and rotated it, it's just going to change when that catapult has to stop, which will change the angle that it shoots the ball. If we move back a little bit, we'll be able to see that happen. And so it's relatively straightforward to set up something like this. So if I make a new scene, if we wanted to create a catapult real quickly, I'm just going to go and create, let's say, a cube. Take this cube, scale it a little bit. I'm going to select this face right there, and in modeling mode, I'm just going to extrude that face. and I'm going to extrude it one more time. I'm going to grab this face right there and extrude that. Maybe scale that down a little bit. Extrude that face out a little. Extrude it again. Extrude it again and scale it down. Extrude it again and move it in. And now we can see that we have this, let's say, arm. For the arm, I'm going to create, let's say, a ball for it to throw. So in the front view, I'm just going to place that right here. And let's get that, let's say, a little smaller. And then basically all I need to do now is let's create a ground plane, which I will scale to be a little bit longer. And then I'll basically take this object, turn that into an active rigid body, turn the ball into an active rigid body, apply gravity to the sphere, so that now when I hit play, we're going to see this. Then I'm just going to select the arm and add a hinge constraint to it. Hinge, create. I will position the hinge over here so that it's oriented correctly. Now when I hit play, and I'm going to turn on wireframe on shaded, we will see this. I will then select the ground and turn it into a passive rigid body, at which point we will get this. I will then create another cube, which I'm going to move over here. And this is kind of just going to be an object which will block how far forward our catapult can swing. That will be a passive rigid body. We're still at this point. And then finally, I will select my arm and apply a spring constraint to it. And for the spring, I'll go to the front view and just move it down here. Then for my arm, I will move its center of mass in Y to move it down, and in X to move it so that the center of mass is beneath this end of the spring, or of the arm. So we can now see where our spring is located. If I now hit play, we will see this. But all I need to do now is take my spring and get its reth lengths to be very long, like a value of 20. Increase its stiffness to a value of 20, so that now at frame 1, my spring is basically compressed. And if I hit play, there you go. A basic catapult created very quickly just by using a spring constraint and a hinge constraint. So that's pretty much the time we have to talk about rigid body dynamics. And so one last thing that I'm going to show is just this little robot guy, just to give you another idea of things that you can do with rigid bodies and constraints. So basically this robot just has a pin constraint between the body and the leg, and then a hinge constraint between the upper leg and the lower leg, another pin constraint between the lower leg and the foot, and that way we can see we're getting a dynamic character. So that if I, let's say, open this other scene in here, I can just go and have this little robot get tossed around and whacked between two different planes. But it's just, again, using constraints on rigid bodies. And there you go.